So in this video we are going to talk about antiderivative of a function and the fundamental theorem of calculus. Let's begin with antiderivative, right? Look at this one. Suppose f and capital F are two functions defined on this closed interval. Then f is said to be an antiderivative of simple f on a b closed interval if f is continuous on a b interval, and when you differentiate uppercase f, then it turned out to be the simple f at some point c, that's c in between a and b interval, right? So let's try to understand. I think most of you know this definition very easily, so let's discuss by using an example. So consider uppercase f of x is sine of x, right? So when you differentiate, we know that sine of x is a continuous function, so it is very smooth continuous function on real line, right? So when you differentiate per case f, what do you get? You get cosine of x, right? So if you define cosine, so cosine as lowercase of x is equal to, let's define cosine of x. So uppercase, when you differentiate uppercase f of x, you get lowercase of x. So therefore this sine of x is said to be the antiderivative of cosine of x, right? This is the simple example. I think you know what an antiderivative is. So now we come to most important theorem here. This theorem is called the fundamental theorem of calculus. And suppose f is a continuous function on closed interval ab, and we define a function uppercase f from closed interval ab to r, right, as this. So let's draw this one. Where's let me get my blackboard, right? So this is our continuous function on ab closed interval, right? So let's define uppercase f from ab interval to real line. So how do we define that function? So consider this curve. So this curve, right? I consider the area of this curve, under this curve, between a and x here. I just only consider the area under this curve between a and x here, right? Now x, this x maps to integral from a to x f of x dx. Let's write that f of x, both are the same, right? So f of x dx, this is our function. So this should be t, right? This independent variable should, let's consider different letter for independent dummy variables, otherwise so we get confused with this x. So dummy variable is t, simple t, right? So capital F, so this uppercase f is a function which is defined as this. So that function goes from this closed interval to real line. So how do we define that function? If you get any element in between these two, these AB interval, in this interval, right? So that maps to this integral of f from a to x. X is an element in between a and b, f of t dt, right? Then we can show this function is continuous on this closed interval, on closed AB interval, as well as f is differentiable on open interval AB, right? You look at this. So if we can show that f is continuous on closed AB interval and differentiable on open AB interval, right? And 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 uppercase f prime of c is same with lowercase f of c. Alright, yeah. For each c in this interval, this open interval, right? So using the previous, we know the definition of antiderivative here. So look at this definition, right? If f is continuous on closed interval and uppercase f prime of c is equal to lowercase of f, then we call capital F or uppercase f is an antiderivative of f. So from this definition we can see that this f is uppercase f is an antiderivative of lowercase f. Right? This is the remark. So by previous theorem, if f is continuous on closed interval AB, then capital F can be defined as this, right? Is an antiderivative of lowercase f on closed interval. So this capital F or uppercase f is an antiderivative of lowercase f on AB interval, right? This one is clear. This is uh, the the fundamental theorem of calculus, right? Think you understand this. So don't we don't give a proof. So we just use these theorems to solve problems, right? If I give more information about this, so here f capital F prime. So this is your capital F, uppercase F, right? So when you take the derivative of this, let's write that one. Then you can understand very easy. So capital F is of x, So this one is clear here. This is a function of x, right? Function of x. So t, simple t is the dummy variable, right? So this is a dummy variable. So capital of capital F of x is this. From a to x, a is an element in between a b interval. So f of t dt, t is a dummy variable, right? So when you differentiate this capital F, that means when you differentiate this capital F, that means this integral from a to x. This is a definite integral, right? Not indefinite, definite integral. F of t dt. If you differentiate this one, so what do you get? If you differentiate this one, so you get simple f of x. So this is called, this one is the fundamental theorem of calculus. So this one is the fundamental theorem of calculus, right? So when you differentiate this integral, right? So x is an element in between a and b interval. So when you differentiate this integral, you get this same function, but the same function f of x, because this is a function of x. So this is a function of x, right? A function. So why this is very important, right? So let's look at this. So all right. So every continuous function defined on this closed interval a b, right? If you define the area under the curve between these two, area under this curve between a and x is a general point in between a and b interval, right? So if you define the integral from a to x f of t dt, so when you differentiate that bit, when you differentiate that integral, the area, when you differentiate the area of the curve under the curve between a and x, you get the same function f. That is important, right? So this is the relationship between integral and differentiation, right? So if you have, so this is the antiderivative of f, antiderivative of f. So when you differentiate this integral, you get the same function here. So let's do an example here. So let's take an example, right? So you are asked to find the derivative of, this integral here. So from a to x, tan cube of t dt, right? So you are asked to find the derivative of this function here. So from the fundamental theorem, right? So when you differentiate this one, this integral, you get the same function here, but the variable, so this is a function of x, the variable, that function depends on x. So what you get when you differentiate this integral, when you differentiate with respect to x, this integral, you get this function here, this function tan cube, and we know that this is a function of x, so tan cube of x. Alright, so alright, so this theorem, this fundamental theorem of calculus says if f is continuous, then it has an antiderivative. Very important. If f is continuous function on closed interval or anything, right? So it has, and we can say that it has an antiderivative, right? So I hope you understood this theorem very clearly. So this week we mainly focus on this theorem, right? So if you go to exam questions, if you look at these questions, this is the fourth question. The first part is use the definition of integral and mean value theorem to show that these things. I think we have done this one before, right? And the second part, find f capital uppercase f prime for each of following functions. I think you can do these things now very easily. So right here, capital F is defined as integral from 3 to x sine of t to the 5 dt. Alright, and this one too. So here look at this, this is defined, this integral is defined from a constant value to x squared. So definitely you have to use chain rule to compute the derivative, right? I think you can do these questions, right? Here there's another question here. So first question, use the definition of integral to show that easy. This is the fourth question, right? And let a be yeah, this one, either this can be done very easily. Look at this one, find f prime, capital F prime, for the following functions. So here, if this function is continuous, the derivative of this one is itself, right? For this, pretty easy, right? If this one is continuous on the interval 0 to infinity, 0 to infinity, no, 1 to infinity, right? So the derivative of this is this one itself. Pretty easy, right? So definitely here you have x squared. I assume this one a little bit here, x squared. So definitely if you want to compute the derivative of this one, you have to use chain rule, right? With the theorem of the fundamental theorem of calculus. Alright guys, I think I will upload the next assignment for you, right? End of this week. Yeah, I will upload that. Think, yeah, that's all today.